So in this section we're going to elaborate a little bit on the mechanism that we described when we were looking at relocation. So we'll expand a little bit, and what we'll try and do is we'll extend our mechanism so that we can now incorporate something called contiguous allocation. So this is sometimes known as memory allocation by partitions, and I think it's pretty self-evident what is meant by that, but I'll describe it for you. So the idea is pretty straightforward. You have this phrase contiguous, where the word contiguous means touching. So it's very simple. When you put a process into main memory, you allocate to that process the memory that it requires in one continuous chunk. Okay, so the main memory then must hold the user processes in whatever number they exist, and also the kernel of the operating system. So you have one partition for the operating system, the kernel, and then another for the user processes. So as we said before, processes have to be protected from each other, and the operating system must be protected from the processes. So that's the model that we're going to use in this section here. And in this diagram, which unfortunately isn't drawn to the standard of the preceding diagrams, but I think it's clear enough for us to be able to discuss, you can see that we have a main memory. So I'll just highlight that. I'll identify the components for you first of all. So first of all, we have a main memory, which is this guy here. So that's this part here. We have our physical addresses, which are represented there. We have our CPU, which is here, and then we have a process, which in this instance is P1. Okay, now what's not shown so clearly is the work of the MMU. When I redraw this diagram, I'll make it totally clear that what we're looking at is the memory management unit, but the memory management unit is everything that's bounded inside this box here. Okay, so you can see there's the relocation register, which we used in the previous diagram, and you can see that the mechanism, broadly speaking, of the work that is done by the memory management unit is the same as before. A logical address is input into the memory management unit, and what emerges is a physical address. Okay, so that's the broad structure of what we're going to do. I'll just remove all this highlighting, and then we'll talk a little bit about what's happening here. So I think what we'll do is we'll start off with what's already familiar to us. So we can see that P1 is executing on the CPU. There's P1 there, and we can see also as well that it is executing a particular machine code instruction, which is add 343. Okay, so that is the machine code instruction add 343, where you have the instruction itself, which is the operator, and then you have the operand. So if we were naive, we might imagine that this is just saying to the CPU, add the integer 343 to whatever value is in the accumulator. But actually what is being said here is to add the contents of the memory address 343 to the value that's in the accumulator. Okay, so anyway, the important point here is that this is a logical address. Okay, and we're not surprised to see that, because that's exactly the model that we had previously. Now for the moment I'm going to ignore the limit register, and instead what I'm going to do is I'm just going to concentrate on the part of the MMU that's already familiar to us. So we can see over here that process 1 is occupying this range of physical addresses, which is 1200 through to 1600. So the relocation register is set to 1200, which represents the first address that is being allocated to P1 in physical memory. So just as before, what we have to do is input the logical address, which is 343, and then add it to the relocation register, and when we do that we end up with 1543, and that is the correct physical address. So the correct physical address would probably be somewhere about here, and its physical value would be 1543, but the logical address that is being seen, executed by process P1 would be 343. So that's great. We can see that that does one thing, which is to translate the logical and the physical address, the logical address into the physical address. So we're not accessing 343 down here, that would be incorrect. And also as well, we can see that in some sense it provides a little bit of protection to our memory spaces. So we can see that, for example, we're not able to access the area of memory down here. Okay, so everything below the value of the relocation register is safe. But here's a different question, which is what is to stop P6 or P1 accessing the address space that belongs to P6? So that's what we have to correct, and that's I'll illustrate this first of all by doing it to show you violation, and then what we'll do is we'll show how an additional feature of the memory management unit prevents this from happening. So I'm just undoing all of the previous annotations. So we're back to the original diagram, and what I'm going to do on this occasion is, instead of us executing the instruction add 343, what I'm going to do is I'm going to delete 343 and I'm going to replace it with a logical address which is 443. Okay, I'll ignore the limit register for the moment, and what I'll instead do is take my 443 and I'll add it to the value of the relocation register, so that'll be plus 1200, and I'll end up with a physical address which is 1643. Okay, now when I annotate the physical memory, you'll see that the logical address 443 actually intrudes into the allocated physical address space of P6. So 1643 is actually violating the principle of isolation and protection, and this is completely disastrous, because effectively what we're doing is we are allowing P1 to access the address space of P6, and this is absolutely not allowed. So this is a flaw and we need to correct it. So what I'll do is I'll undo the annotations that we've just created there, and we'll repeat the exercise, except this time what we'll do is we'll incorporate this second register, which is the limit register. So we still have our faulty logical address, which is 443, but this time when the logical address 443 is input, when the logical address 443 is input to the memory management unit, what we can see is that it's first of all checked against the limit register. So the first check that's performed is this limit register value, which is 400. And you might say, well, where does that 400 come from? Well, if we look at the size of the allocated address space for P1, we can see that it is 1200 through to 1600. So the overall size of that portion of memory is 400, and that's where the 400 comes from. So the test that's done is that the logical address 443 is tested against the value of the limit register, and the test is it smaller than the size of the limit register? So you can see here that when we evaluate 443 and we test it against the value of 400, we can see that it is not smaller than the limit register. So at this point, when the memory management unit is presented with a false output when that expression is evaluated, what it then does is it ditches the entire transaction. Okay, so this evaluation here has turned out to be false, and consequently the course of action that the memory management unit takes is to terminate the execution of the machine code instruction add 443, and it generates a special type of error which is known as a trap, which is an addressing error in this particular instance. And what that will do is it will wake up the kernel. The kernel will examine the contents of the various registers inside the memory management unit, and it will say, okay, this is an attempt to breach a fundamental principle of memory management. We can observe that this process P1 is attempting to access an address space that does not belong to it. So at that point, what the kernel will do is it will terminate completely P1. So in this world of addressing errors, there is no gradation of punishment. If you do something wrong as a process, then you get terminated. Now, if we undo that and annotate again, and we go back to the original address space, or the original logical address, which was 443, you can see that we end up with something that's slightly different. Okay, so if we do 343, which was the original logical address, and we compare it against the value of the limit register, which is 400, you can see that 343 is obviously less than 400. So the flow of control passes through the check provided by the limit register, and we then proceed to the mechanism provided by the relocation register. So at that point, what we do is we add the logical address to the limit or the relocation register, and that gives us our new physical address, and that then gets communicated to the hardware of the main memory. So that's okay. That's an example then, if you like, of a second correct translation of memory, a logical address to a physical address. So what we've seen is that the relocation register protects the address spaces below the process that is executing a particular machine code instruction, and the limit register protects the address spaces of the processes above the executing process, and that's quite clever. Now, this type of operating system, or this type of memory management system, is used in very, very simple time sharing systems. So these are pretty archaic, and obviously the memory has to be managed by the kernel of the operating system. So if you were thinking about how to do this, then it would make sense that if every process has its own contiguous block of memory, what the operating system then has to do is to keep a track of processes which need allocated memory. So this is what we'll see on the next diagram, where we have 5 processes which are ready to be allocated main memory. You can see, as normal, they have their identification number. You can see also that they have memory requirements, and you can see that for the sake of convenience we're specifying a period of time that they're going to be in main memory for, so that might be 10 milliseconds or 5 milliseconds and so forth. So we can then represent this graphically, and you can see this in the next diagram. So what we're looking at, and again I apologise for the quality of the diagram, I need to redraw it. but we're looking at a physical memory, and what you can see is that at the very top we have the kernel of the operating system loaded into main memory. So the first address of main memory is up here, which is 0, like so, and then thereafter you have the rest of main memory occupied by processes. So we can see that the state of the main memory is represented in 5 different snapshots. So we have A, we have time B, C, D and E, like so. Okay, so this is our diagram, and what we can see is that at time A we have 3 processes loaded into main memory. We have P1, P2 and P3. The pink area that you can see here is empty. Okay, we can see that P1 is using up a contiguous chunk of memory which goes from 400 kilobytes to 1000 kilobytes. P2 is taking up 1000 kilobytes from 1000 through to 2000, and P3 is taking up 2000 through to 2200. So what we imagine is that a little bit of time passes and P2 terminates, it finishes whatever it's doing, and it liberates a chunk of physical memory from 1000 through to 2000. So the next process in the queue is P4. So what the operating system does is it says, okay, P4 wants to execute. I need to find a chunk of memory which is free and large enough to accommodate the memory requirements of P4. So it sees the newly vacated chunk of memory from 1000 through to 2000 kilobytes, and it allocates P4 into that empty chunk. So we can see that the consequence of that is that we now have an empty space from 1700 through to 2000, and there's another empty space from 2200 to 2560. In the next snapshot, which is D, you can see that P1 terminates, and that liberates a hole in main memory which is 400 through to 1000, and you can see that the operating system says, okay, I have an incoming process P5 which has a memory requirement of 500 kilobytes. Is there a space in main memory that will accommodate this process? And it turns out that there is, from 400 through to 1000. So P5 gets allocated a chunk of main memory from physical address 400k through to 900 kilobytes. So now the issue is that we have a chunk of free memory here, a chunk of free memory here, a chunk of free memory here. Now if we look at each of these, we can see that the size of memory that's available here is 100 kilobytes, 300 and 360. Now if we insist that every process has to be contiguously allocated, which means that it goes into main memory in one chunk, right, that has a beginning and an end, then you can see that this is going to cause a problem for us. And the problem is that we have chunks of memory which are only going to be suitable, which are only, we have chunks of empty memory which are only going to be suitable for certain sizes of process. So if, for example, we have P6 coming in, and P6 has a size of 90 kilobytes, then obviously we can stick it in here, okay, because that chunk of free memory is big enough to accommodate it. But if we have another process, let's say it's P7, and its size is 400 kilobytes, well, we've got a problem, because this empty chunk here is only 100, it's not big enough, and this empty chunk here is 300, and it's not big enough, and this empty chunk here is not big enough because it's 360. Now this is not, this is very problematical, because if we add these free chunks together, we could say, okay, we've got 100 plus 300, that's 400, plus another 360, that's 760 kilobytes of available memory, which if they were aggregated together, they could then easily accommodate P7 with its memory requirement of 400 kilobytes. But that's not possible because we're insisting upon contiguous allocation. And you might say, well, okay, I wonder, could we not just move all of these empty spaces up to the top of main memory? So would it not be a good idea to just shift them up, okay, and then all the pink areas would bubble down, if you like, to the bottom and create a new free chunk which would be 760 kilobytes in size. And that seems like a decent enough idea, except that it's not a simple matter of just moving these guys about in main memory. They would actually have to be copied out to the secondary storage disk and then moved up, copied back from the secondary storage disk into a new memory location. So that absolutely wouldn't work, because every time you go near the secondary storage device, there's going to be a phenomenally significant slowdown in the overall efficiency of your system. So this is really as a solution to the problem of multitasking, where you have processes that are being moved about in main memory. This doesn't work. It just isn't flexible enough. So we'll summarize that by looking at the next couple of slides. So the next couple of slides talk about, could we allocate more efficiently? There are different algorithms for doing this, but none of them are particularly satisfactory. That's essentially the content of slide 31. And then in terms of slide 32, we introduced the idea of fragmentation. So fragmentation is just the idea that there is sufficient space to satisfy the memory requirement of a particular process, but because it's not contiguous, we cannot allocate that process into main memory. There's another type of fragmentation which is called internal fragmentation. You don't need to worry about that. And then I alluded to the idea that you might be able to shuffle memory contents to place all free memory together in one large block. That's not really a possibility, and the reason why it's not a possibility is because you'd have to involve the secondary storage device, and that's extremely slow in terms of what needs to be done. So there is a solution to this, right? And the solution is to have a mechanism for memory management, which is paging, and that's what we'll address in the next section.